Hello, this is the third video in the preliminary series on sets, permutations and combinations for OCR Discrete Further Maths. You will have met sets and Venn diagrams at GCSE, but if you followed another international syllabus previously, you may wish to look at those topics in more depth after this video. Here are some commonly used set symbols and notation. For example, this symbol is an element of, with a dash through is not an element of, is a proper subset of, the null or empty set, the universal set, and it's worth noting the distinction between is an element of and the symbol for the universal set. A dashed or A not, the complement of a set A, so anything that is not in A, union, and an intersection. You also need to be familiar with this notation. So N for the set of natural numbers or counting numbers, Z to represent the set of integers. You can see that this includes 0 and positive and negative integers. Z plus, so just the set of positive integers. And if also we include 0, it's Z plus with a 0. R, the set of real numbers, Q, the set of rational numbers, and C, the set of complex numbers. If you haven't done the complex numbers topic yet, don't worry about this one too much at the moment. Here we have used the brackets and the subscriptions of 1, 2, 3, etc. to show a set with the elements x1, x2, and so on. Symbols and notations should just be viewed like the abbreviations you probably use a lot when you're text messaging. If used, you will remember them very quickly. If we look at this Venn diagram, we can see that this rectangle box represents everything of the universal set, and this circle might represent anything in the set A and this in the set B. You'll note that the intersection is the overlap here. So, in this particular instance, we would say that A has got the elements of 1, 3, 4, 5, 7, and 8, and B is the set of 2, 3, 8, and 9. You can see that 3 and 8 are in both A and B. The 6 is in E, but not in A or B. So if we know what is in A, we can then also say what is not in A. So what is not in A would be the numbers 2, 6, and 9. A together with B, or union B, will have all of the numbers except for the 6, which lies outside both of them. A intersection with B, the numbers in both A and B will be 3 and 8. Numbers in A together with numbers that are not in B. So in other words, if this area is B, the not in B, so this is in, this would be, all of this would be B. But the numbers then not in B would be the 1, 4, 5, 6, 7. But together with the numbers with A would then include back the 3 and 8. So 1, 3, 4, 5, 6, 7 and 8. And then none of A intersection with none of B would simply be the 6. We can therefore look at these statements and see which are true. So, is 2 in B? Yes. Is 3 in not A? No. Is 6 in A not intersection with B? Well, none of A would have the 6 in, but the 6 does not lie in B, therefore is no overlap between A not and B that includes a 6, so that's a no. See that 6 actually is in A union B not, so that statement is false, and A overlapping or intersecting with nothing in A would indeed be empty. If we want to refer only to the number of elements in the various subsets, we use n bracket. So, for example here, we would have that n of A union B would be 8 numbers. And the total number in the whole universal set would be 9. N of A in this case we can see is 23, so in other words for 10 plus the 13. And N of B not would be for 10 plus the 4, which is 14. Another result worth remembering is the inclusion-exclusion principle for two sets, which states that the number of elements in A union B equals the number of elements of A plus the number of elements of B minus or subtract the number in the intersection A intersection B. In other words, we would not want to count those 13 elements of the overlap more than once. Here is an example. 35 teenagers were asked what takeaways they like to eat. So in other words, the number of elements altogether is 35. 24 of these answered Chinese, 16 answered Indian, 10 answered pizza. None of the teenagers liked all three, and all of those who liked pizza also liked Chinese. So the question is, if all the teenagers liked at least one, how many liked only Indian? This is a suitable question to solve with the aid of a Venn diagram. We could draw the pizza as a subset of the Chinese, but another way of doing it is to draw 3 subsets for those who like Chinese, those who like pizza, and those who like Indian. We know that in total we have 35. We know that nobody liked all 3, so that would be a 0 there. We know that all 10 of those who liked pizza also liked Chinese, so therefore those 2 elements or regions will also be a 0. So the real unknown is this overlap of who liked both Chinese and Indian. We know the total amount of Indian was 16, so I'm going to call that 16 minus x there. And therefore, of the 24 answered Chinese, 10 are already accounted for, which leaves 14 then minus x, the unknown. In order to solve for x, we know that 14 minus x plus x plus the 16 minus x plus the 10 must equal 35. If we take away the brackets and sort all of that out, we will come to the fact that x equals 5. Thus we can see that the number that only liked Indian is 16 minus 5, or in other words, 11. Here is a different type of example. 3 people, Alex, Brian and Claire, let's call them ABC, are going on a fairground ride, and each carriage can take 1, 2 or 3 people. Now, empty carriages are not allowed, but it doesn't matter in what order they travel. So in how many different ways can they join the ride? Well, we could put them all in one carriage. Or we could put 2 in one carriage and 1 in the next, in which case A could ride with B or with C or separately. However, they may wish to all ride on their own. There are 5 different ways in which 3 people can join the ride. Actually, what we're really looking at here is how to split a set of 3 items into non-empty subsets. So, looking at partitions of sets, a set can be divided into 1 or more non-empty subsets in lots of different ways, and these are called partitions of sets. So, in answer to the question, how many partitions are there of the set ABC, we found there were 5 in the last example. This answers an enumeration problem. When we are partitioning the sets, there are several notations in use, 2 of which are given below. We're mostly just interested in the total count, so we just need to be consistent, and we'll choose the second, slightly simpler notation option. Moving on then to consider the partitions of a set of 4 items. You can see that there are various options. First, that each of the items takes, if you like, a single carriage or is a subset on its own. So A distinct from B, distinct from C, distinct from D. Or that 2 of them are put together. In which case, how many of options are there? So only 1 for that if they all go separately. Here we have C and D travelling together. But of course, we could have looked at BC travelling together, or indeed AB travelling together. But additionally, we could have B travelling with D, or A travelling with C. There are 6 of these options. If we look at putting them in pairs, we have here the option A, B and C, D, but of course AC could go together, leaving B and D together, or A could go with D, leaving BC together. So there's only 3 of those options. If we have the 3 and then the 1, you can probably see that there would be A could go with B and D, leaving C on their own, or B, C, D could go together, leaving A on their own, or we could have A, C, D, leaving B on their own. So that would give us 4 options. And then there is only one way of them all 4 travelling together. Altogether, this adds up to 15 possibilities. Now, I found the number of each type by careful listing, but I could have used some ideas from the work on combinations. We will be looking at combinations in a couple of videos' time. In the next video, 1.4, we'll be looking at permutations.